For those of you who've been here for the last talk by Lior, he talked about all these kinds of tools for monitoring. And here we're going to touch about how the monitoring tools are currently not enough and what we can do with machine learning in order to enhance the monitoring of logs. So, about myself. I'm 31 years old, scientist at heart. I have a master's degree in neuroscience, information processing from Bar-Ilan University. And currently, I'm a co-founder and chief scientist at Coralogix. So what do we do in Coralogix? Coralogix is a machine learning platform that analyzes your log records. Of course, that log management is already included. We have the indexing, the querying, the filtering, alerting that you are used to in your current tools. But on top of that, we have an analytics platform that turns your data into patterns and flows. And then we can give you deep insights on your system and, of course, automatically alert you about production problems. In this talk, we will explore the challenges of software logs today. We will take a not so short overview of machine learning of some of the use cases, suggest a fully automatic algorithm for anomaly detection in logs. So, what do we use log records for? Debugging, security, compliance, user analytics, we all know that. But specifically, there are two use cases that stand out. Production monitoring and production troubleshooting. 70% of users of these systems use log records for production troubleshooting. Additionally, open source software and cloud enables companies to grow very, very fast, and their data and log records grow exponentially. Even small companies are generating enormous amounts of logs, and they have trouble of actually finding what they want. And the data grows exponentially. The big data approach up until now, and also in log management, is to collect everything. Let's just dump everything into a single bucket, and then we can do whatever we want when we need it, and we'll know what to do. Or will we? The assumption is that in the belief that a sufficiently large pile of horse shit, we will find a pony. Just collect the data, and you'll find something interesting in there. The problem is that it is not that simple. What we have now is that humans have to tackle these enormous amounts of data. And this is a problem because we are very bad at identifying complex relationships in our systems. We're not noticing small but important changes. And also, we're never 100% in focus. This causes a main issue that most of the time, on investigating issues, we're actually trying to find what the issue is, what caused it, and what do we need to fix. 70% of the time is for finding the problem instead of fixing it. We can condense all this into the problem that log management does not have a brain. We need log management to think for us and to have all these correlations automatically recognized in order to give us where the problem is so we can focus on fixing it instead of taking 70% of the time just to find where the problem is. So let's give it a brain. This is the log analytics. But before we dive into it, let's have a quick overview of machine learning. What's machine learning? It is a field of study that gives computers the ability to learn by themselves instead of being explicitly programmed. This is by Arthur Samuel, the pioneer of machine learning in 1959. In traditional coding, what we do mainly is that we have a model of the world, of how the world works in our head. And then we write code that explicitly represents this model and behaves exactly like we expect it. And then, whenever the world changes, or the model of our head changes, we need to manually update the code in order to reflect that. The concept of machine learning is that you have loose concepts of what the world behaves like. And what you do is write code that can automatically learn a model of that world and then behave accordingly. The exact behavior of the code is not always known, but the general results are pretty good. And it can also be updated automatically as the model knows how to build the representation of the world by itself. How well does it work? First, it is very quick, much faster than what we can do and humans do. And sometimes it even has better accuracy. What types of machine learning do we have? Supervised machine learning deals with data that is clearly defined. We have a right and wrong answers for each of our input data. We let the machine learn from these right and wrong answers in order to predict what will be the answer for data that it has not seen yet. The two main types are regression and classification. They are both they both try to predict the outcome of a specific data point, with regression using continuous values and with classification using classes of discrete values. So what is regression? We can take the temperature of the day and data of the amount of yogurt sold in order to predict what the temperature is based on the amount of yogurt that someone sold in the store. And a linear regression will give us a pretty good accuracy for this data set. Another example can be given the cups of coffee that are sold every 10 minutes and predict how many cups of coffee will be sold on any given time of the day. Linear regression does not always solve our problem. As we can see, the data does not behave in a linear way, but a polynomial solution here gives a pretty good accuracy for how much cups of coffee are sold in every time of the day. For classification, can we identify the type of an iris based on its leaf sizes? We have 3 types of irises, and each one has 2 types of leaves. The question is, can we identify which kind of iris is it only by the sizes of the leaves that we have? So we have 4 measurements, the width and the length of the 2 types of leaves that each iris has. And now we need to plot the data and see whether we can cluster these units in order to predict correctly according to the leaf size. Fisher's iris dataset, which is one of the most classic in machine learning, it has 150 measurements of each of the 3 categories of irises. And when we plot one of the sizes of the leaves, the width against its length, we can use a support vector machine, one of the clustering algorithms, in order to paint the zones that we will predict each of the types of an iris. This method alone gives us 73% accuracy, which is pretty good for something that is completely automatic. Reinforcement learning is a different type of supervised learning, and it is reward-based, which means that we need to define a set of rules that shows us the interaction of the machine and the world, where each action can be good or bad and will increase or decrease the reward that the machine gets. And the machine tries to maximize this score. It is used in game bots and in recommender systems. And specifically, if we go for a recommender system, we can build profiles for items and users. We then can recommend an item to a user based on his previous preferences. And we gain rewards when users click on these recommended items. Accordingly, we can update the model all the time in order to have all the correlations of new data and new users. The most renowned recommender systems are implemented in YouTube, Netflix, Amazon, where you get suggested of what the next movie you will see, what the next show you should watch, or what book you should buy. But the general rule is that recommender systems try to offer similar things to similar users. For example, if we take Jim, who likes sports, and Jim likes to buy pizza, salads, and Coke, and we have Bob, that also is into sports and likes pizza and salads, we need our system to recognize that they are similar users and offer a Coke also to Bob. And the percentage of success here will be quite high the more good the recommender system is. Unsupervised learning is a different kind, and it attacks a problem that we have with supervised machine learning. The problem is that it gives good results, but it requires us to have a lot of labeled data. And labeled data is quite sparse, and we don't always have the good and bad answers for these data. Labeling for unlabeled data, if we want to label that data, it is a human effort which takes a lot of time and a lot of energy. In unsupervised learning, the machine automatically recognizes the relationships in the data, and it has no right or wrong answers. It does it automatically. And then we can use it in order to use a supervised learning algorithm on base of the features that we've learned on a supervised learning. Some approaches in unsupervised learning include clustering algorithms, anomaly detection of rare events, and the buzzword of the year, deep learning, where in deep learning, the idea is to study from a lot of non-labeled data, learn highly non-linear correlations, which can then represent complex relationships inside our data, and it gives surprisingly good results for many applications. So we'll take an example about how deep learning works, but we're not going to dive deep into the math, because otherwise we'll spend the whole convention here speaking just about that. So can we automatically cluster digits together? The idea is to have, we have 60,000 black and white 20 by 20 pixel images of handwritten digits. And we want our computer to understand which of these images belongs to which representation of an image, of a digit. We want it to recognize that these threes, although they are not the same image, they should be classified as threes. So each image, which is 20 by 20 pixels, we flatten it to a 400 floating point values vector. We take this vector, and then we can feed it into a neural network. The neural network consists of an input layer, where all these input values are inserted into this layer. Hidden layers over here and here, we have several of them, and they recognize features inside these images. And the output layer is the only supervised thing that we have here. We will probably have for digits 10 supervised output layer output neurons in the output layer, and then we can know from each neuron which cluster the image came from. After feeding an image to an input layer, the neural network automatically learns the features of that layer. And each neuron lights up when it recognizes a certain feature in the layer that is previous to it. If we look at the first layer, one neuron can actually recognize round edges, the other one will recognize vertical lines, another may recognize diagonal lines, etc. And then these neurons will actually light up whenever they recognize such features in the previous layer. And each layer learns higher representations of the layer that is before it. So if we look at the whole process here, we have the neural network. After it is learned, we give it one vector of representation of an image of 1. Feeding it to the input layer, we can now see that several features have been recognized, and they are lit up, and they feed forward these activation neurons onto the next layer. And there, another feature is recognized, until the output layer recognizes that the features that the last layer has recognized fit the digit of 1. This neural network actually became an expert in recognizing different features of how digits are represented in the world. It it can find that 8s are actually have confined zeros that are stuck together. And it will, and many times find the 8s and 0s may find themselves clustering the same features, but the output layer will differentiate them by finding these features. They feed forward the vectors from one layer to another, and each layer just recognizes different features of the previous layer. So this layer, basically, yeah. This layer just found that these vectors, when these light up, these two neurons light up, it causes this neuron to activate. Because the features that it has found is a vertical line and another feature of something else, which is a black surrounding, for example. Yes, but each number is a feature. It's a feature in its own. Okay. Yeah, that's the basic idea. This method can actually get an amazing 0.2% error rate, which is amazing. It is better than what humans do on this data set. Okay, so getting back to log records, how do we apply all these methods in order to improve our monitoring? We want to tackle several problems. One is that log data is very redundant. We see a lot of instances of the same logs, just with different parameters inside, which we know they're of the same type, but it's hard for a machine to recognize this. Additionally, the data is so abundant that finding the rare events and the important events is very hard. Additionally, when we look at systems that users interact with or have complex components inside, each action is represented by several log records. And then, looking at the flow of records, we have many unrelated events just coming all the time from different actions happening in the system. And tracing the complete sequence of logs of a single action is very hard. The solution is to identify log prototypes or log templates. Cluster which logs represent an action, alert when actions are incomplete or anomalous, and notify about new errors which have never occurred before, because now we know which prototype each log is. And we can know that a new log error prototype has arrived to the system, which you should be notified about. And there is, of course, much more to see. So a real-world example. This is an occurrences graph of all the logs that a B2C system emits. Each column here represents a different log type. The frequency here is the ratio of this log type to all the other logs. So this log comes at around 9.8% of all the time. The color represents the severity of the log record. And we can see that the 10 most frequent log records comprise of around 60% of the data. Cutting around here, most of these log around between 1 and 10%, and a lot of the data is redundant. We almost always miss all the long tail that we see here. Now, a good machine learning for log management would give me statistics about these. These are my core business in my system. These are mostly info logs of reporting actions that users or machines are doing. And it will also be able to alert me on these rare events, which mostly comprise of critical errors and warning logs that I'm most likely missing. So we'll have correlations on these ones, and then statistics, and alerts on these ones. Okay, possible log analysis pipeline. I'm going to warn you, brace yourself. Math is coming. So the idea is we want to cluster similar log records into log prototypes. So we have these just different kinds of logs and different and similar logs which are I still don't know they are of the same type. So we need to find a distance metric to compare two log records and tell me that they are similar. After that, we create a new log template from these similar log records, and then we can even identify the variables inside these log records in order to find statistics of how these variables react. For example, if we have these two log records, creating tag on stream -1 position 42 and log 2, everyone here in the room who's looking on this understands that this is the same log template. But comparing these is, of course, giving us a false in a strictly coding scheme. A different solution may be to look at the single words of each of these log records and compare them. And then we can find that most of the words are actually similar and can be found in both logs, but I'm not sure if this is distant enough or close enough in order to be clustered together. And this approach is also poses a problem. And comparing all these substrings of all the logs in my system is an extremely expensive operation. So what we're going to do, we're going to find a heuristic distance metric that will take a log record, break it into the words that it has, and then through hashing of locality-sensitive hashing, we will receive a binary representation of a log record. And this binary representation can now be used in order to be compared to all the other logs, but in a very quick way of bitwise operations, which are the quickest kinds of operations that a computer can do. And now we only need to construct this thing once for each log, and we can compare it many, many times to many other log records. This process gives us that these two logs are actually the same log prototype, and they have two variables at these locations where the dissimilarities happen. The result is that of m log records, we get n prototypes, where n is much, much smaller than m. M is in the billions of log records that our system creates every day, but the total amounts of log prototypes that we actually create are 900, 1,000 for large systems. After having our log prototype, we can now collect the values that these variables have and find a distribution that best represents the behavior of these log records and these variables inside them. After we find the distributions, we can now define the bands which are anomalous in the behavior of these logs, and then alert on whenever these variables jump out of the normal behavior that we expect from this log record. Additionally, we'll want to find what sequence of logs represent an action in our system. So how do we find sequences? We want to find logs that correlate together, that come together, in order to find sequences that are related. So we'll assume that logs are independent. That means that two logs can come one after another in a random fashion. And if we find logs that break this assumption, then it is probably that because they are related together. Two actions that come one after another will break our assumption of independence because we will find them a lot of time. This is called the G-test, and it is about the observed amount of occurrences that we found of sequences against the expected. And it is a statistical test that can show us when have we broken an independence assumption in order to take these and understand that two logs are related or a sequence is related. Let's take it into a real-world example. If I have a purchase request come into my system, I then need to get the cart of that purchase from the database, process that request, authenticate the payment, maybe update the BI system and another one, send a response also to the client after I've processed it, and then probably have a log that marked this purchase as complete. Following the template search that we've defined in the beginning, we actually have here not 8 but 7 different kinds of logs, because update BI system 1 and system 2 is actually a very similar log that is just reported in the same way. And now we want to count all the sequences of length 2. We'll call them 2 sequences. L1, the log template 1, and log template 2, the purchase and get card, are a frequent sequence, 2 sequence. And we expect to never see, or almost never see, a 2 sequence which comprises of purchase request and authenticate payment. These will happen rarely, only when 2 actions happen one after another, and the actions come into the same time, where one purchase is just begun and another purchase already authenticate the payment, so we'll find them one after another. But mostly, L1 and L2 will be the frequent sequences that we find. After mapping all the possible 2 sequences that we have in our system, we need to normalize their scores, which means that if we found 1,000 times the L1 and L2, and other sequences have been found several times but much lower, we'll subtract the average of these occurrences and divide by the variance. And now we have a normalized score of how frequent or how related these sequences of logs are. When we have the normalized 2 sequences, we can now take each of the sequences that we found here and try to lengthen them to a 3 sequence, add another log record, and then try to find if they are still frequent in our system. When repeating the process, we're taking K sequence and trying to convert it into a K+1 sequence. And we're doing this as long as the g-test scores tells us that we're still breaking the independence assumption, and the normalized score of the K sequence is still smaller than the normalized score of the K+1. In this way, we receive all the sequences of length K which are correlated in our system. And now each action is represented inside our system as sequences that we can follow, and we can find statistics about them, we can look into the variables that they have, etc. So if we look at the log sequence, a 3 sequence with ratio 1, 1, 1 would say that we expect that each log prototype has the same occurrences of all the others. In our example here, we have 7 sequence with 1 log record showing twice. So we expect the ratio of this log to be twice as much as the others. When these sequences are now broken, we need to count how many times they are broken. And if these are broken by a certain ratio, and the p-value, the statistical significance of this is high enough, then we will alert that there is an anomaly. Because no one is interested in a sequence that is broken once. It is probably just a network malfunction or something, or a different username, password that wasn't inserted right. There are many sequences that break all the time. But if it goes to a significant level, then you probably have an error in your system. And you will be notified it in real time. Additionally, software is constantly changing, which means that we will be updating the model all the time as long as these sequences continue to come. And there is much more that we haven't explored here. For summary, everyone will analyze their big data with machine learning. There is no other option. We just have too much data and we cannot handle it. However, it is hard to do by yourself, but if you do it, it is extremely rewarding, and you can customize it to exactly what you want and what you need. And most importantly, you can focus on the products that you want to build and you want to support instead of the bugs that are inside them. Thank you. If you have any further questions, you can, I'm available here, and you can send me an email and visit our website to see how we implemented such a method and what we can do with Coralogix for your log records.